Hi all. We're going to get started soon, probably just another minute or so. So if you just don't mind hanging tight in there, we'll get started soon. So probably about another, I'd say 2 or 3 minutes. All right. So we're going to get started here. Increase the size. There we go. Okay. One second. Trying to see what is consuming so much memory here. Okay. So last class we started. We had a few discussions. We were discussing research objectives, how we solve problems. We were also discussing. We started to discuss, or we got into and finished up on logic and hypothesis development. How does one construct an argument? What are the different types of logic that are out there that we commonly use? So we had, we discussed all of those topics the other day in class, and we started to talk about data. And so at this point in our course, we are shifting over away from some of the definition theoretical stuff into more of the practical data analysis material. And so before we get into any of that, we're going to have a discussion just on data. So we started yesterday to get a little bit into data. We're going to finish off this lecture, and then we should be pretty much up to par on the schedule. Okay, so the homework that's going to be posted on Saturday will pretty much cover everything that we talked about this past week, including today. Today's virtual lecture, I'm going to do a little differently. I'm not going to take live questions. You can feel free to shoot me over some questions after the lecture. Be more than happy to answer them. So just hold on tight to them, and shoot over an email to me if you if you have any questions. All right. So the data analysis process. All right. So when we're given a data set, we need to analyze that data set. Okay. Well, first we have to ask, well, what is data? We can think of data as in the colloquial sense, as basically any piece of information. Now, in our context, data simply refers to the values that are assigned to the individuals for each and every variable that we have in our research project. So the data, when we get it, as I had mentioned before, is usually stored in a table. And the table, general formats, the standard usually, is that rows represent individual responses and columns represent groups of responses for a single variable. Now, each row in a data set needs to be unique. That is, we can't have duplicate rows in a data set. There needs to be some type of distinguishing factor. That is, if we had a person and we only surveyed that person once in time, we cannot have a duplicate entry of that same person in our data set. We would need to remove that. The only caveat to that is if we had surveyed that individual at 2 different moments in time. Okay, so here we have this notion of data as being stored in a table with all of those, basic dynamics at work. Okay, so now, data is often stored in one of 2 ways. It's either stored in a series of spreadsheet files, or it's stored in databases. So a certain level of knowledge is often required when you're analyzing data, when data is given to you. Of course, you need to clean that data, and you need to summarize data sometimes before you actually get to the analysis, the full-on analysis phase. So having a certain knowledge or level of knowledge of spreadsheet software, as well as possibly database querying languages, goes a long way. It helps in being able to easily analyze data, prepare data for analysis. In this course, I'm just going to assume that all of you have a basic knowledge of just spreadsheet software, rather than going full on and assuming that you have some level of knowledge of databases. That type of knowledge tends to be a little bit more intricate, and you tend to require them for more advanced, complex type of data sets. In our course, we're just sticking to pretty much more simplistic types of data. And so we're going to just focus mostly on, or assume rather, that all of you have some level of knowledge of spreadsheet software. What do I mean by that? Being able to open up a data set in something like Microsoft Excel or Google Sheets, being able to manipulate that data set in said software, possibly using formulas to summarize data. And that's pretty much the extent of knowledge that I'm expecting you guys to have, at least in this course. But when you get out into the real world, having a knowledge of database, how to operate within a database, normalize a database, query a database, all those skills help elevate your ability to quickly get or acquire and summarize or prepare data for the analysis phase. So once you get data, you usually go through a process to analyze that data. That process involves a few different steps. First, we do something called clean the data, which I'll get a little bit more into in terms of some of the aspects of that. Then we do something called coding the data, which is not computer programming, but it's translating some of the data values in the data set to other values, and we'll get into that in a moment. You then run through something called a descriptive analysis. If you need to, you then run through something called a causal analysis. If your data had come from a sample, then you would be running through something called an inferential analysis. And last, you interpret all of the results of these different types of analysis. Now, out there, you might find that there's other types of analysis. You might come across the word predictive analysis or abductive analysis or anything along those lines. probabilistic analysis. These type of analysis on data is sort of just outside the scope of our course, and so we're going to avoid an entire discussion on them, at least in our class. So for now, we're going to just focus on the three basic main types of analysis, which are descriptive, causal, and inferential. Those other types of analysis that you'll see coming across, that you might come across, are usually examples of or consequences of one of the three types of basic analysis that we'll talk about today. So I'm not actually going to go through the entire process of each of these steps. That's somewhat what the rest of our course will focus on. The remainder of our course will focus on how do you conduct a full descriptive analysis on a data set, how do you conduct a causal analysis on a data set, and how do you conduct an inferential analysis. And those steps, they're, excuse me, pardon me, they're all interrelated to each other in some sense. We'll get more into the details as this remainder of our course continues. So the first step when you get data is, of course, to do something called clean it. Most software that you'll use to analyze data requires the data to be what we call clean. All right. Now, remember that raw data is a common form of data that's often presented to any researcher. That is, when a researcher obtains data, very rarely is that data itself clean. That is, there might be inconsistencies, missing values, inappropriate values that were not in line or are not in line with the definition of a particular variable. So as a result, if you were to just take that raw data set, plug it into your software and try to analyze it, your software is really it's going to get confused. It's not going to know, what to do. As a result, you need to clean it. Okay, so what does it mean to clean data? It means to ensure that data is consistent according to the definition of the variable. Consistent meaning if your variable is a numerical variable, then you need to ensure that the values in the data set are within the proper ranges. For example, if you have a variable called age, let's say, you need to ensure then that you don't have any negative numbers, you don't have zero. If your population comprises of only individuals above the age of 30, then you need to remove all individuals that are less than the age of 30. All right, that is, you need to ensure that all the values that are in the data set meet the definition of your variable. So if you say age is a variable in my data set, but I'm only allowing values of the variable age to be between the age of 30 and 60, then you need to eliminate all possible entries in the data set that lie outside that range. If, on the other hand, your data is categorical, then you need to ensure that the values are all the same based on how you've defined the categorical variable. Remember that a categorical variable is a variable whose values are potential categories. That is, when you define the variable, you're only allowing certain categories in your definition. Okay, so in this for this case, let's say you have region. Let's suppose you only allow 4 values: north, south, east, and west. Well, you need to ensure that all of the values that are in your data set are one of those 4 values in the same exact form. That is, these are technically the same value, south and south, but the way the computer reads it is it sees that these two are actually quite different. This comprises of all caps. This has the first letter as capitalized. So when you define your variable, you need to ensure that the names of your categories are all consistent, standardized, and that when you get your data set, the actual data itself follows the same values that you've defined. So if you defined region to only be north, south, east, west, where only the first letter is capitalized, Then what you need to do is go on and fix all of these values to ensure that there's consistency across. So this is an example of an inconsistent data set. This is an example of where you have fixed those sort of inconsistencies. So you'll notice that north was converted over to north with a capital N. South was converted to south with only a capital S. This was consistent with your definition, so that doesn't change. New Jersey is a state, not even a region, so you have to match up which value in your variables, best match with this value. In this case, it would be north. And central was a value that fit within the definition of your variable. So everything now looks good in this example, and you would then go off to analyze this data set. Okay? Sort of. The next step is to actually do something called coding. So one of the biggest concerns with having categorical data in a data set is that it actually consumes a lot of space. If you only have a sample size of maybe 100 to maybe 1,000 individuals, really not that big of a deal. But in today's day and age, we do have data sets that are actually quite in the higher millions, if not billions. And so each character that we have as a value in our data set consumes computer space. And when we store our data in terms of characters rather than numerical values, it just creates a drag on the computer itself, both in terms of storage and in computation. So when we actually go and try and store the data, the computer is going to store it, going to have a massive amount of space. Instead of storing this in terms of just, let's say, 1 byte, and I'm not saying that that's the actual amount, but let's say instead of just 1 byte with a single number, you would now have to store it in 1, 2, 3, 4, 5 bytes just for that character, just for that one value alone. So if you have, in other words, a data set that is, if you were to code all of these and the data set's 1 gigabyte, the non-coded version would actually be 5 gigabytes. So in other words, non-coded data is nothing more than a waste of computer space. So most times when you have a data set, you should have it coded. You should replace the actual categories with numerical values. The other advantage to doing so is in terms of computation time. When a computer tries to sort a data set, let's say you wanted to sort your data set by region, where you list all the rows of your data set based on whether, all the north, then the south, then the central, then when you do that, the computer is going to take a really long time to sort that data. Had you had represented all the numerical values, all the categorical values with just numerical labels, and that's all these are, just labels, then the computer takes a little bit of a shorter amount of time in order to actually sort through different data sets, as well as summarize different pieces of data. So, moral of the story, whenever you have a categorical variable for any categorical variable, it's just good practice to convert the actual hard categories over into just numerical values. Now, don't be confused here, because this is not an actual conversion that you're doing. You're not actually converting a categorical variable to a numerical variable. It's still treated as a categorical variable. The only difference is the categories are just simply represented by numerical labels. So you got to be careful with that distinction. All right. So you can't, just because you do coding doesn't magically turn this variable into a numerical variable. You're still analyzing it as though it were a categorical variable. So rather than finding the average region, which makes no sense, you would just find the percentage of individuals that responded with 0, the percentage of individuals that responded with 1, and the percentage of individuals that responded with 2. And notice from here and the prior that we basically just swapped out these values with numerical values, and we basically created a little reference table so we know what each numerical value is actually representing. So good practice after you've cleaned data is to, of course, code your data. Once the data is clean and coded, you want to move on to an actual analysis of the data. So there are two basic types of analysis, really a third, but two fundamental types of analysis that any analyst or researcher usually seeks to conduct. The first type of analysis is what's often referred to as a descriptive analysis. And it's just that. You're just describing the overall makeup of your sample, and that, or if you have population data, then your population. This type of analysis is conducted on usually a variable by variable basis. That is, let's say you have 10 variables in your data set, then you're going to conduct 10 different descriptive analyses on each and every variable in the data set. A majority of descriptive analysis pretty much comes down to just simply calculating statistics if you have a sample data, or parameters if you have population data. How do you know which statistics and parameters to calculate for a descriptive analysis? Well, it depends on the type of variable that you have. If you are conducting a descriptive analysis on a categorical variable, then what you're going to want to do is compute percentages or proportions or counts. Usually what you do is compute something called a summary table. A summary table is a complete representation of a categorical variable for the data that was given to you. That is, you're going to go through each and every each and every category that's defined for that variable and count how many individuals responded with a value for that category. So for example, if I were doing a categorical analysis on the variable region, what I would do is count how many individuals responded with 0, how many individuals responded with 1, and how many individuals responded with 2. When I take that information, those counts, and then divide by the total sample size or population size, if we have population data, we get something called a proportion, which represents the relative magnitude of presence of each of these categories. So in the summary table, in this case, would look like 0, 2. There's 2 occurrences of the category 0. 1, 2. There's 2 occurrences of the category 1. 2, 1. There's only 1 occurrence of category 2. We would then take that. The next step in constructing the summary table would then be to convert the 2 to 1 to percentages. Here we have a total of 5, so that we would convert the 2 to 2 over 5, right? We would then have 2 over 5, and then we would have 1 over 5, which of course, that is 2 over 5, of course, is 40%, 2 over 5 is 40%, and 1 over 5 is 20%. So we would say that 40% of individuals responded with region 0, 40% of individuals responded with region 1, and 20% individuals responded with 2. Okay. So that is how we conduct a categorical descriptive analysis for a single categorical variable. So again, we count the number of individuals that responded for every category. We divide each count by the sample size or population size if we have a population. And then we multiply each proportion by 100 to obtain a percentage. We then record each result for each category in a table. And the resulting table is what's referred to as a summary table. We then, of course, for a visualization, could draw a bar chart or a pie chart to get some visual sense of the structure of our data. Now, when we have a numerical variable and we would like to conduct a descriptive analysis on that, what we would need to do are a few different things. Unlike a categorical-based descriptive analysis, we can actually calculate certain statistics and parameters based on numerical values. That is, we can calculate measures of central tendency, measures of dispersion, and distributional-based measures. Usually, we do so by calculating the mean and median. Remember that I said the mode is usually not frequently reported. Every now and then it is. The range, the standard deviation, and the variance of the data set, of the variable. Usually, we calculate something called the first and third quartile. I'm not going to show you how to do that by hand, but I will show you how to do that in R once we get to our lectures on R. And then you use you calculate last something called a relative frequency distribution table. I know that sounds like a lot of words, but think of that type of table as a summary table for the numerical variable. Basically, what you're doing is converting the numerical variable into a categorical variable and then taking the same steps as a categorical variable to calculate a summary table. It's basically the same idea. Usually the way that there's a lot of different ways you can construct this. One way, for example, could be to first choose a number of categories you want to split your numerical variable into. For example, suppose you have the variable age, and you know that ages range from the age of 20 to the age of 80 in your data set. You want to somehow break that variable age up into different age categories. You can do that by first looking at the maximum and the minimum. Here in our example, we have 80 and 20 for a total range of 60. And let's suppose that you want to break that interval up into 10 respective age groups. I'm sorry, 6 respective age groups. So you would take the 60, divide by 6, and you get a length of 10. So each age group would be separated by 10. For example, you would have 20 ages from 20 to 20 plus 10, which is 30. 30 to 40, 40 to 50, 50 to 60, right? So you would therefore have, in that instance, all of those different categories. Again, 20 to 30, 30 to 40, 40 to 50, 50 to 60. Okay, so I said 6, which is technically 5. You would then count, all right, how many individuals responded with an age where that age was between 20 and 30, where 30 is not included. Do the same thing for all the other categories. Basically, take the same process as calculating a summary table. As a result, you would then divide each count by the sample size or population size, and you get what's called a relative frequency distribution table. It's basically a summary table for a numerical variable. The difference being that there's some notion of order to the categories themselves, unlike a categorical variable, which may not have any notion or sense of order. So that's basically a descriptive analysis. At the end of the day, you're just calculating means, variances, medians, standard deviations, first and third quartiles or quantiles, calculating relative frequency distribution tables, and for categorical variables, calculating something called summary tables, just to get an overall picture or idea of how the data set is structured on a variable by variable basis. So next, we move to, once you do that, if you have any hypotheses that you've proposed, you need to then test those hypotheses. Usually, the list of hypotheses are well defined, and as a result, we need to test them. remember what we discussed yesterday in regards to hypothesis development. We had mentioned that a hypothesis is a well-justified statement, justified in the sense on two fronts. First, on the deductive front, meaning you can go to the past literature, find theoretical relationships between the different variables, and from there, use the laws of deductive reasoning to argue the truth of your hypothesis. The second part of justifying the truth of a hypothesis is seeing, well, in what context does the hypothesis hold true, and in which context does it not hold true. In that case, you need to basically take your observations and summarize them and test if your hypothesis is true or not true. Or I should say, the probability test what is the probability, or find what is the probability that your hypothesis is true within your population, or what's the probability that it's not true. Now, as simple as that may sound, it's actually quite complex. And the type of analysis for testing these type of hypotheses are often referred to as causal analysis. Causal analysis basically comprises of a set of tools that attempts to find, does this cause that? If this is true, then that is true. Okay. In other words, you're testing if implication-based statements are true or not true in the population that you're studying. So, when you test for a causal connection between variables, the thing to remember that's the utmost importance is that the methods of testing actually rely on a set of well-defined hypotheses. That is, the actual process that you take to analyze your data to see, is there what we call empirical justification for the hypothesis or not? That depends on how your data is structured. If your data doesn't meet certain assumptions of the method that you're using to analyze the data, then you can't use that method, right? I know that sounds kind of strange because we said assumption making usually happens in analytical research, and that's true. But we're not technically making any assumptions. What we're doing is testing if the assumptions of a particular method of analysis is true or not true. Now, the way that works is based on a few different assumptions that we'll talk about later in this course, mostly something known as the heterogeneity-homogeneity assumption of our population. And then from there, depending on the method of analysis that we pursue, to analyze a potential causal relationship, we have to take different methods of analysis for different scenarios. We'll find later that in more complex cases that we'll actually have something more complex than just saying, does A cause B? In some scenarios, we'll have something much more complex, like does A, B, C, and D, when taken together, cause E? We might have enough time to explore those cases, but in terms of just very simple causal analysis, that is determining does A cause B? Under those type of scenarios, we have four basic cases. And it really comes down to whether the variable in the if statement, what we call the independent variable, is categorical or numerical, as well as what is the type of variable for the dependent variable, something we call the dependent variable. That is the variable in our then statement, part of our statement. Okay, so we have, with that in mind, we have four different possibilities. Categorical to categorical, categorical to numerical, numerical to categorical, or numerical to numerical. And depending on what we're testing, what our scenario is, what our hypothesis looks like, we then notice we then can determine which method of analysis to pursue based on the particular scenario we have. We won't cover the methods of analysis today, but this is basically the overall process. So, for example, if we're trying to determine does region cause income, okay, region would be an independent variable, and that would be categorical. Income would be a numerical variable, and so we would take whatever method of analysis is associated with this scenario, right? Does, again, region cause income, right? Does another example, does coffee brand preference cause, these coming up, does coffee brand preference cause, I'm sorry, does gender cause coffee brand preference? Does your gender determine whether or not you prefer a particular brand of coffee or don't prefer? So you would look at each of your hypotheses, look at the variable in the if part of it, look at the variable in the then part of it, determine what types of variables those are, and then go to each of the one, see which scenario it is, and then take that method of analysis. The method of analysis that you pursue in a causal analysis, however, you may not be able to actually even take that method of analysis. You would actually have to do something called assumption testing on the data to determine if that method is appropriate or inappropriate. And we'll get to that later in our course. So those are the basics of causal analysis. Put simply, you're just testing. Does A cause B? And how do you actually test that with the data that you have? You don't test it by, the one thing that I can stress is that you don't test that by just looking at charts and graphs. That's not a way of doing proper causal analysis. You can't just look at a graph, see a pattern, observe a pattern, and say, yep, A causes B. That's not how we do proper causal analysis. And there's a few reasons for that we'll discuss later in this course. But the one thing that I sort of want to clear up right now, which seems to be a big misconception in just sort of everyday type of data analysis that people seem to do, I should say incorrectly, is to look at a chart and say, yes, this chart seems to have a pattern, therefore there is a relationship. Well, no, not necessarily. And the reverse is also true. You might look at a chart where there first may appear that there's no relationship between two variables, but given the type of method of analysis you're undertaking, you might actually find that there is a relationship between the two variables in certain contexts. So with that all in mind, the moral of the story here is visualizations are not a way to properly analyze data. They can go a long way in helping you understand data and lead you as a compass to determine what method of analysis should I take. But by no reasons ever should you ever look at a chart and say, yes, I see a pattern, therefore there's a causal relationship. Not a proper way to analyze data. Okay, so we'll get more into that when we get to our causal analysis portion of our course. Now, if you have population data, then you need not worry about something called inferential analysis. You can just conduct a straightforward descriptive analysis and causal analysis, and you would pretty much be done. On the other hand, when you have sample data, which a majority of the time analysts do have sample data, you're trying to somehow use the data within the sample after conducting a descriptive analysis, and in some cases after, usually it's during, but after conducting a causal analysis. You want to somehow take those results and say something about the overall population. When you do that, the method, rather, that you're taking to actually do that is what we call inferential analysis. As the name implies, you're inferring something about the population by using information that's selected from the sample. Now, there's two main ways of conducting an inferential analysis. There's The first way is through the use of what we call confidence intervals, and the second way is through the use of what we call hypothesis testing. Never, and let me stress this, ever do we just take a single statistic that we calculated and say, yes, this is an approximation to the parameter. While that is technically true, the problem with that is that is called a point estimate. For example, if you were trying to predict what tomorrow's stock price is going to be for, let's say, Apple, you probably would not just want to calculate a single number. Your investors would probably get mad at you because most likely you're going to be wrong. So, for example, Apple's trading at, I didn't check it last, I think it's like 170 a share, and you come up, you do your analysis and you say, I'm predicting that it's going to go to $171 per share tomorrow, right? And that prediction, in a sense, is what's called a parameter estimation. You've calculated a statistic based on a sample, okay? So the problem with that, however, is that you can't just say, okay, yes, it's going to be 171. A point estimate is most likely going to be wrong. Actually, it's overwhelmingly most likely, usually like a 99.9999 whatever percent probability that you're not going to be getting your statistic to exactly equal your parameter. Therefore, just calculating statistics is not enough to approximate a value of a parameter. Another analogy, you're trying to find out what is the average age of let's say, of a Starbucks consumer. Well, you're obviously not going to be able to collect data on every single Starbucks consumer, and so far it's impossible to calculate that number directly. So of course you have to resort to sampling and statistics. But if you were to take a sample of Starbucks users and calculate, or consumers, and calculate the average age, and let's say it's 34 years old, it's probably not the case that the average age in the population is 34 years old. In fact, you're probably wrong about that. So the process of using that 34-year-old age to estimate the real average age in the population, or similarly, the process of using the $171 prediction to estimate what Apple's going to trade at tomorrow is not a good method of inferring something about the population. Instead, what you would want to do is, instead of giving a single estimate, you would want to give a range of estimates. That is, I can tell you, you're probably a lot less confident. Your manager would probably be a lot less confident in you if you told them, you know what, the average age of a Starbucks consumer is 34.4 years old. Because that manager knows there's no way you could have gathered that information from every Starbucks consumer. They would feel a lot more confident in your approximation if you said, okay, I'm 95% certain that the average age of a Starbucks consumer is somewhere between 33 and 36 years old. And I'm just shooting the numbers out there, random numbers. But that's sort of the moral of the story. Right. So instead of saying, okay, yes, the statistic, that is the average age in the sample, but that may not be the average age in the population. And as a result, you need to somehow take that 34 years old together with your sample statistic, your sample size, as well as some other information about the formula that's used to calculate the statistic, use that information in a meaningful way, leveraging what we call probability theory, to construct a range of numbers that you believe the real value of the parameter lies within a certain degree of probability. There's still a chance you'll be wrong, but at least that chance is minimized. And at least you have a better chance of being correct than just simply stating, oh, the average age of a Starbucks consumer is 34. Well, I can assure you that I'm fairly not confident in your estimation at all, versus your statement saying the average age, I'm 95% certain the average age of a Starbucks consumer, somewhere between 33 and 36. That's a much more confident statement to make. On the other hand, if you're doing some type of causal analysis, most of the time you're not trying to calculate confidence intervals, but you're rather trying to test if the causal association it actually holds true in the population. That is, you're usually trying to test, is my hypothesis correct or is it incorrect when given my population? Now, again, you can easily determine if your hypothesis is correct or incorrect if you had just sample data or if you had just population data. But if you're trying to say something about the population using sample data, then you need to actually take that information from the sample and conduct what we call a hypothesis test, which proposes your hypothesis that you've justified in a mathematical way and determines whether or not your hypothesis is correct or not correct. Hypothesis testing and confidence intervals are actually the same approach mathematically. There's no mathematical difference between these two methods, but they're conducted differently. That is, the process of going through these different methods differ, despite them leading you to the same result. Hypothesis testing usually makes sense for when you're trying to conduct a causal analysis. Confidence intervals make sense for when you're conducting a descriptive analysis. So here's the moral of the story. First, you're doing a descriptive analysis on your sample. Then you're taking the results of that descriptive analysis and conducting an inferential analysis on the population to make final descriptive statements about the population, okay? So, for example, if you've collected information on age and income and you have a sample, you might have calculated the following statistics: average age, average income, standard deviation age, standard deviation income. But those only are statistics, so they only represent the sample. Your goal is to say something about the population. That is, you want to know what's the average age in the population, what's the average age, what's the average income in the population, what's the standard deviation of age in the population, what's the standard deviation of income in the population. So the way that you conduct that type of descriptive analysis is through the use of inferential analysis. You're taking the results of a descriptive analysis in the sample using confidence intervals to finalize your statements descriptively about the population. So in your sample, for example, you can say, well, my average age in my sample is 34.3 with a standard deviation of 5. And then you would then take that somehow, calculate confidence intervals, and conclude, but the average age in my population, I'm 95% sure is somewhere between 32 and 36 years old. And the standard deviation of that, I'm fairly certain, is somewhere between 4 and 6. So populations, when you're doing an inferential analysis from sample data, you're giving ranges of values. For descriptive analysis for samples, you're just calculating statistics. When you're doing inferential analysis for causal analysis, most often what happens in practice is you're actually conducting both at the same time. You're actually doing this is a little bit different than conducting the descriptive analysis first, then doing an inferential analysis. When you're doing causal analysis on the population, you're actually simultaneously doing causal analysis and inferential analysis at the same time, as strange as that sounds. That is, very rarely are you doing a causal analysis solely on the sample, taking the results, and then inferring about the population. That's not what happens. What you do is you actually simultaneously conduct the causal and inferential analysis. In this course, I'm going to show you how you can do a causal analysis assuming you had pure population data. And the only reason I take that approach is so that you understand what it actually means for two variables to be causally related to each other from a data perspective. However, in practice, and we'll move on later to this in our course, very rarely will you do that. In fact, never will you do that. You'll always conduct a sample-based causal analysis. And in some cases, many argue you even do that, even if you had population data. Nonetheless, That is inferential analysis. Again, put simply, inferential analysis is the process of taking information that you've gathered about your sample and drawing a conclusion about the population. And the way in which you're doing that is either through calculating confidence intervals, which mostly you're doing for descriptive analysis on the population using sample data, or hypothesis testing, which most of the time you're using for causal analysis, again, on the population. The last step is to summarize your results. The results that come out of your analysis, both descriptively and causally, and in some cases, if you take the next step, predictively, are just a whole bunch of, jumbled numbers. So what you need to do is basically take those numbers and tell a coherent story about your population. After all, at the end of the day, that's what you are as a data analyst. You're a translator between what the theory and data suggest into the more practical implications of how you should use that information. So you have to think of yourself, the analyst, as basically a translator between all of the mathematics and numbers that come out of your analysis and the layman who may or may not understand anything about statistics. So the last step in your data analysis is to essentially take your results and view all of them within a singular and cohesive narrative or context about the population. And so that might involve describing the population in great detail. Now, there are always going to be limitations in your data analysis, whether those are assumptions that you can't test due to the type of data that you have, or you have too small of a sample size, or you're missing variables. The one thing you have to recognize is that there is no such thing as a perfect data analysis. You're always going to have some type of mistake or error. And in fact, you can give the same data set to two different analysts, and they'll spit out two different, numbers or results. The one thing you have to keep in mind is that statistics is a license to tell a story, but the question is whose story. Okay, so that's what you have to be very mindful of when conducting a data analysis. So a lot of it involves a certain level of subjectivity, despite your attempts to be and remain objective, which we all hope for. There's always going to be a certain level of personal bias and personal subjectivity that's injected into the analysis. Think about it this way. If there weren't, you wouldn't have so many different types of analysts on Wall Street trying to predict where a stock is going. You wouldn't have so many different economists that disagree with how just a general economy should work, or for that matter, what a particular policy and its effect on the overall economy will be. Or you won't have so many scientists or physicists that disagree with each other in terms of certain theory about or regarding just general physics. The moral of the story is that you're going to have different perspectives, even from the same exact data set. But that's okay. So long as you understand that you took the proper and moral and ethical steps that are involved in the analysis that are in line with the theory, and so long as you offer a careful explanation of any errors in your analysis, then you're in the clear, so to speak. Okay. So that concludes our lecture for today. Now, we still technically have about 15 minutes. I'm going to cut the lecture a little bit short. In terms of R, okay, you can get R at the website that I provided on the syllabus. Please ensure that you go to the syllabus and try to download it. The installation does differ for Mac versus Windows. I will go through a step-by-step procedure on how to go about installing R when we get back into class on Monday. Please remember that we do have an assignment that is going to be posted. This will be your assignment 4. Remember that everybody on assignment 3 just gets a straight 100. On assignment 4, that will cover all the material that we had discussed this week. It will still only be 10 questions. But just keep in mind that it's just a little bit extra lecture material since we had missed in assignment 3. So with all of that said, please make sure you keep an eye out for it on Saturday. On Monday, we will do an in-class workshop that will involve all of what we've discussed. I might actually even push that off to Wednesday just so I have some sense of consistency between the 2 sections here. And I think I might actually do that now that I think about it. Nonetheless, I will automatically assign all of you to groups. I'll let you know what those groups are when we get into class. For anyone that cannot make the workshop for whatever reason, you should send me over an email so that I can give you either an alternative assignment. But you do need a legitimate excuse for missing our class. Again, that's going to be held on Wednesday. I've changed my mind on that. Not Monday, but on Wednesday. Okay, so I apologize for the shift there. We now technically are pretty much fully back up to speed in terms of the lecture material. So we're back on schedule. So if you have any questions, please shoot them over to me. I'll be on tomorrow morning, of course, during my virtual office hours, and I'll be more than happy to respond to any questions that any of you may have. All right, well, thanks for taking the time to watch, and I will see all of you on Monday.